Hi, I'm Hyungjun from KAIST. Today, I will present our paper, By My Eyes, Grounding Multimodal Large Language Models with Sensor Data via Visual Prompting. Sensor data includes various measurements from devices like smartphones, wearables, and IoT systems. They are used in a wide range of ubiquitous applications, ranging from healthcare to environmental sensing. Sensor data shows wide range of diversity across different sensor devices, users, and tasks. So one of the open challenges is building a foundation model that can generalize across this diversity. However, achieving this is difficult because of the strong heterogeneity across different settings, and the expensive cost of collecting such diverse datasets is also challenging. Here, large language models offer promising potential. With their world knowledge across different domains, including the sensor applications, LLMs provide a new way to interpret and solve sensory tasks more generally. So, how LLMs can handle sensor data? Typically, sensor data is represented as numeric sequences with multiple channels. One approach is to insert this data directly into the LLM's text prompts. However, there is a problem. Real-world sensor data often results in very long sequences, but the existing work mostly focuses on short sequences, which can lead to performance issues and high costs in the real world. There have been attempts to shorten these prompts by extracting key information from the sequences, but this approach requires expert knowledge about the sensors, making it impractical for broader use. Sensor data usually involves lengthy sequences. For example, when sampled at 100 Hz, just 10 seconds of sensor data results in 1,000 digits. So to explore how this lengthy data affects LLM performance, we conducted a preliminary experiment to see if LLMs could handle simple tasks using varying lengths of sequences. So we focused on two different basic tasks. The first task was an arithmetic operation, where the LLM had to predict the mean value of a random synthetic sine wave. The second task involved pattern recognition, a binary classification where the LLM had to distinguish between a sawtooth and sine wave. The results of our experiments are shown in the graphs. The error linearly increased as the sequence length grew longer for both tasks. It's important to note that the maximum sequence length here was only 500 digits, which is much shorter than the typical sensor data. This clearly highlights the challenge of handling long sensor data with LLMs. At the same time, using sensor data as text in LLMs results in very high costs. For example, continuous 3-channel sensing with 100 Hz for just 1 minute produces 18,000 digits, and this leads to 90,000 tokens per minute. It means that if we use GPT-4o API with this for an hour, it would cost around $450 for continuous sensing, and it demonstrates how expensive it can be to handle the sensor data in the real world. To address this, our work introduces a new approach, grounding multimodal LLMs with sensor data through visual prompting. Instead of representing sensor data as text, we propose a method that automatically generates visualized plots of the sensor data and then used to solve tasks with multimodal LLMs that take image inputs. Let me first introduce how we designed our visual prompt. This figure provides an overview of the design. Here, instead of using numeric sequences in text, we represent the sensor data as visualized images. We leverage the in-context ability of multimodal LLMs by incorporating the labeled few-shot example images. In the images, we specify both the label information and the visualization method. The target data is simply labeled as target data. We also include the text prompt. The text provides instructions and descriptions about the data and task. This combination of text and the visual prompts allows the multimodal LLMs to better understand the context and handle the sensor data effectively. A challenge that comes with our visual prompt approach is how to generate the visualizations. To create a practical solution that non-experts also can easily use for various tasks, we propose a visualization generator. It uses multimodal LLMs as agents for autonomous data visualization. The multimodal LLM leverages public visualization libraries to generate tailored visualizations based on the specific data and task descriptions. Here is the overall prompt used by the visualization generator. We divide the processes into two steps. The first step is visualization tool filtering. Note that our final goal is to select the best method by observing the visualized images themselves, not just relying on the text descriptions. This approach helps avoiding bias from the descriptions and capturing the true characteristics of the data at the hand. However, there are too many visualization methods available in the public libraries, and testing all of them would be costly. To reduce the cost, we start by filtering out visualization tools that fit the purpose based on the data and task description first. This helps efficiently identify methods that highlight meaningful features. The prompt for this step includes details about the available tools and the descriptions about the data and the task. We also include demonstrations of the filtering process using some example scenarios. The result of this tab is a smaller set of filtered visualization methods. After the filtering, the next step is to select the best method from the remaining ones. Here, we generate the visualizations using all the filter tools, and the multimodal LLMs observes them and performs a self-assessment for determining the most appropriate one. The prompt for this step includes the visualization results, instructions related to the filter tools, and descriptions about the data and the task. The outcome of this process is a single final visualization that we use in our visual prompt. From this step, we aimed the multimodal LLMs to account for subtle variations in the user behavior, environment, or device settings, which are the factors that may not be fully captured by the data and task descriptions alone. To evaluate the effectiveness of our approach, we conducted experiments on 9 distinct tasks across 4 different sensing modalities. We used GPT-4o as the multimodal LLMs to solve these tasks and compared both the accuracy and the number of tokens with the text-only prompting approach. The main results are shown in the table. All the experiments used one-shot example. When comparing our visual prompting approach to text-only prompts, we observed a 10% performance improvement on average, which consistently worked better for all tasks. Additionally, the text-only prompts required a large number of tokens with most of the sensory tasks. In contrast, our visual prompting approach used significantly fewer tokens. On average, it was more than 15 times fewer than the text-only methods. Note that the token counts for the visual prompts here includes the images following the token counting logic of GPT-4o. We also conducted experiments by varying the number of examples. While adding more examples did not consistently improve performance, the key takeaway here is that the visual prompts consistently outperformed text-only prompts when using the same number of examples. An interesting observation here we made is that in some cases, the number of tokens were similar between the visual and text-only prompts, yet the visual prompts still achieved better performance. This suggests that the advantage of visual prompts is not solely due to the reduction of token counts, but also from the effective use of visual information itself. We evaluated the effectiveness of our visualization generator by comparing it with 2 other baselines. The first baseline used a fixed method. It was a simple waveform plot, which is the easiest option to choose. The second baseline selected the visualization method by solely on the data and task description, without our visualization selection process. The difference here is that this approach doesn't observe the visualized results to choose the best option, and it only relies on the text descriptions. So in the table, you can see that while the baselines experience significant performance drops for specific datasets, our approach maintains strong performance across all the tasks. For example, when applied to ECG data, the raw waveform plot was not effective. However, our visualization generator created an individual heartbeats plot, which was effective for the task and led to a 9% improvement. Similarly, when applied to the accelerometer datasets, the description-based approach selected spectrogram plots, which wasn't really effective for the data and led to large performance drop. In contrast, our visualization generator chose the raw waveform plot, achieving significantly better performance. To wrap up, those are the key contributions of our research. First, our research proposes an approach to ground multimodal LLMs with sensor data by providing visualized sensor data as images and achieved improved performance at reduced cost than the existing text-based baselines. Next, we present a visualization generator that automatically generates suitable visualizations for various sensory tasks using the public libraries. Lastly, we conducted experiments on 9 different sensory tasks across 4 modalities and demonstrated the broad applicability of our research. So that was all for my presentation, and if you have any questions or feedback, feel free to contact me via email. Thank you.